All right, guys. So this is going to be the first video in the metals and metallurgy notes. Now, I'm going to break this apart into a look at how we refine metals and then actually a closer look at the properties of metals and how we describe them. So let's just jump right in. So metals are really, really important things to modern society, right? We use them in everything from airplanes and cars to cell phones to computers, right? The components of the headphones that I'm using are, metals. There are components in, I mean, pretty much everything on my desk has some component associated with it that's a metal. And we get our metals from the Earth's crust, right? From the lithosphere. Now, we don't unfortunately find these metals in their pure forms. A lot of those metals are found in inorganic compounds as a component of an inorganic compound, and we call those minerals. So, some of the ones in the book that are pretty cool include malachite, magnetite, and cinnabar. Cinnabar is a great source of mercury. Magnetite's a great source of iron, and there are many, many, many different names for these things, all right? But they are usually named by common names. They're not usually named by their chemical names, all right? Now, there is a list of those chemical compositions for the minerals. Malachite, great source of copper. Um, corundum, good source of aluminum. Sphalerite is a great source of zinc. Like we said a minute ago, cinnabar is a great source of mercury, right? There are many, many, many different minerals that you can get your specific metals from. You don't need to memorize these. They're just there for your kind of information. Now, metals themselves come from a lot of different places all over the world. We do live in a global society, right? I think your book mentions the fact that cobalt, or about half of cobalt, comes from um, a relatively unstable region in Africa, Congo and Zambia. But it's certainly worth noting that when you study chemistry, it's easy to get lost in the atoms, right, and the ions and the molecules and all that, and forget the fact that, at the large scale, the people who are utilizing this knowledge of chemistry are acting in a global market. So, it is worthwhile to note where these things come from. So, this graph gives us a percentage of, or not a percentage, an amount of usable ore that comes from each country. You'll notice that the United States actually doesn't have quite as big a slice as you might have thought it would have, right? So a lot of our metal comes from other places, all right? Now, when we talk about metallurgy, okay, we're talking about mining. We're talking about concentrating our ores, okay? We're talking about reducing those ores to get the free metals and purifying them. And then finally, we're talking about making alloys because, metals are useful. Iron's great, all right, but steel's better. You're not going to find steel laying around on the ground, though. You got to make it. So a lot of times we purify these metals and then we finally get a product that we can work with, and we add some other compound to it or some other element to it in order to make sure that it has the um, the final properties that we want. Now, one of the ways that we process ore is pyrometallurgy. Pyro means at high temperatures. Okay, so pyrometallurgy is the use of high temperature to alter or reduce a mineral. One of the ways that we do that is calcination. If you see this little symbol right here, right, this delta, normally you're thinking, oh, that means change. Well, when it's over top of an arrow, it actually usually means addition of heat. And calcination is a great example of a reaction that would have that there. So you can calcinate something, right? So you heat the solid in order to decompose it into maybe two different parts. And usually you're doing that because you want to eliminate some product. In this case here, we've got a lead 2 carbonate, it looks like. And when you calcinate it, it breaks down into lead oxide, lead 2 oxide, and carbon dioxide gas. Now, this gas is obviously going to leave. So if you think about the process in terms of refining a metal, you have a less useful starting product, but after you heat it, you now just have an oxide of lead that you can then process to free up your lead. Roasting, all right, is another reaction where you are going to basically cook your ore, and there's going to be a reaction that occurs between the furnace atmosphere, which is usually oxygen, and the ore itself. And this is different from calcination. Calcination is a decomposition reaction that is kick-started by the addition of heat. Roasting is a reaction between the ore itself and the atmosphere of the furnace. So you can see here two different roasting reactions that we have going on. The first one is, I guess that would be MO is what? Molybdenum. So molybdenum 2 sulfur, no, that'd be 4. Molybdenum 4 sulfide is reacting with oxygen to produce this oxide of our molybdenum and a sulfur dioxide. Now, this is convenient because this is a gas, so it's going to leave. You're going to be left with this metal oxide. With the mercury sulfide there, which I guess it would be a mercury 2 sulfide, it's going to react with oxygen, and it's actually going to leave you with mercury gas, which if you're trying to refine mercury, that's a great thing to have, right? You've done it. In kind of contrast to roasting, you have smelting. Smelting is a process where you're going to end up with layers of products, so they're both going to be in the liquid form. And slag is the byproduct of this. It's usually one of the layers. It's usually a silicate compound, and you can actually find slag here in our area. So if you go out to Goshen Pass and you kick around in the rocks and you find a bluish kind of rock, it's got like a real shiny, it's almost like a luster. It's like a glass-like sheen to it. That is potentially some slag from back when they used to cook iron in the upriver from Goshen Pass. Lowmore had a furnace, Longdale furnace, right, which is nearby us. And I'm trying to think, I know there's another one. Oh, it's escaping me at the moment. But there are quite a few furnaces around that used to be involved with smelting. All right, so we can find some slag around here sometime. Now, refining is another word that we use when we talk about getting ore ready for, purification. It's the treatment of crude, impure metals in order to improve its purity or define its composition. Now, these 4 words are not interchangeable, right? Make sure that you know which word you're using to describe a specific process. Now, I am going to focus in on iron, all right, and the function of a blast furnace. I'm going to mention hydrometallurgy. I'm going to talk about leaching. I'm going to barely touch on electrometallurgy in this chapter. We study electrochemistry later in the year, and I cover leaching in first-year chem. So I'm really going to focus the remainder of this video on this blast furnace because I think it's really important that we understand how we get the iron that we use. All right, so iron itself is usually processed from hematite or magnetite. You can use some other ions, but those are the most common. Now, a blast furnace, sorry, is an ingenious setup. Okay, it has what we call a charge at the top. Okay, this is the charge. And this kind of funnel-shaped region is where the charge is inserted into the blast furnace, all right? And I'm going to leave that label there, actually, the charge, okay? And the charge is, it's not just adding fuel, right, to the furnace. It's not just adding iron. It's actually adding things that are, what's the word I'm looking for here? It's late. I don't know if you guys can tell that. It's like 11:45 at night when I'm making this video. Sorry. The word has escaped me. It is integral to the setup of the blast furnace that the charge comes in through the top, and I'll show you why. So the ore is self-explanatory, right? This is where our source of iron is coming from. The limestone is really important because the limestone is going to form our slag. It's going to be our binder, all right? Um, and the coke is the fuel, and it's also the reducer, okay? So as the charge enters the blast furnace, right, and it falls into the blast furnace, there are reactions that are going to occur at different levels, at different temperatures in this blast furnace. So at the very bottom, we have this, I guess it would be like a combustion zone. It's really, really hot. It can get up to around 2000 Celsius, might be running around 1600 if this is in this instance, but I know that it can reach 2000. And at this point, you're going to have hot air blasted in. So here's a source of oxygen. So you've got 1600 to 2000 degree temperatures, a big blast of oxygen, and you have coke falling down into the blast furnace. Now you might be asking, what is coke? Well, coke is a coal product. It's like 90, 85-ish percent, 90%, maybe a little more percent carbon. So it's a great source of fuel. And as it breaks down, one of the byproducts of the burning of coke is carbon monoxide. And carbon monoxide is our reducer here. And this is really important. And this is cool. So the carbon monoxide, I'm going to switch my pen color here. I'm going to blue. The carbon monoxide that's produced here, obviously it's hot, it goes up. And as that carbon monoxide interacts or rises, it's going to encounter the ore that's falling. So the Fe2O3 or the Fe3O4. When it does that, it's actually going to liberate the iron, and the iron is just going to fall down to the bottom where it's going to be heated up and it's going to melt, and you're going to end up with this layer of molten iron at the bottom. Now, some of the iron is not going to quite make it all the way down, or sorry, some of the iron is not going to immediately split. It's going to keep falling as, hematite or whatever. And as it gets down there, there's going to be some free carbon that also does some reducing. There might be some H2, some hydrogen that does some reducing, but the main reducer is that carbon monoxide gas. Now, while we're down here looking at iron, I want you to notice this person down here that's drawn to scale. So a blast furnace is huge, right? We're talking maybe 10 meters across at the base here. So like we're talking like 30 feet or so there. We're talking maybe, 30 or 40 meters tall. This is a big, big reaction vessel. Now, there's a lot more detail about what happens at each layer. I think some of it's in your book. You could certainly look at more of it as you go, or if you wanted to, like if you want to do some research. But this hot gas that goes out, right? And because again, everything in chemistry at the industrial scale is about being effective, being efficient, saving money, that kind of thing. Well, this gas right here, this stuff is hot, right? And so usually we pipe it through a filter, a, a filter, there we go, like a particulate filter. And then that hot gas is going to actually warm the air that is then blown in there. So it's like reused, right? So the heat there is being reused. And then it actually goes to a stove where it can be used to process some other things, right? So it's, a closed circuit kind of thing. Now, it's not by any stretch of the imagination pollution free. This is going to produce slag. This is going to produce sulfur dioxide. This is going to produce carbon dioxide. It's going to produce nitrogen dioxide, all of which are certainly pollutants, but this is the current way that we make iron or pig iron. So at the bottom, our purified iron is going to exit. We skim the slag off and go from there. Like I said, carbon monoxide and hydrogen gas are going to act as our reducing gases in this process, but carbon monoxide is certainly the more important of the two. Now, I will point out one more historical thing here. I don't know if you've ever heard of something called pig iron before, but when blast furnaces were made on the smaller scale, they would have channels running out of them with ingot casts right at the bottom. That was a really terribly drawn three-dimensional ingot cast. kind of like that. There we go. Okay, and people thought this was like the sow, and these were the piglets, and it looked like they were suckling right at the sow. So the iron would, flow out, and it would fill up these iron molds, and so that would become the pigs. And so casted iron ingots were called pigs, and so we get pig iron. So if you ever see pig iron, now you know where it comes from, right? The blast furnace. Now, iron is really useful. We use it to make steel. Problem with that iron, though, is that there are still some impurities that are present. Certainly some silicates, certainly some manganese, phosphorus, sulfur is present. All that carbon that's floating around in that blast furnace, some of it gets dissolved. And so if we're going to make steel, we need to get rid of those things. In order to do that, we put it in this converter. This is called a converter, right? Not really a cool name there. But the converter it houses this molten iron, and the steel maker, the steel worker, whatever you call those folks, they're going to insert air, or not air, sorry, oxygen, into this converter, and they're going to monitor the amount of oxidation reduction chemistry that goes on. And when they are, certain that most of the impurities have been removed, they'll tilt the trunnion and pour out the steel, and there we go. We'll pour that into molds, and then you have your steel. When they pour it into the mold, just consequently, right, because technically at this point, right, when you're pouring, it's still iron coming out, right? Iron out. When they pour it into the mold, this is when we're going to add elements to make the steel. Now, obviously, basic steel is just carbon, right? So we have iron atoms in some kind of lattice. All right, we'll draw this one. There we go. All right, so there's our crystal lattice of iron. All right, and the carbon just sits in these little windows, and that's what gives us basic steel. You can add other things, though, to it in order to make your steel have specific properties. So that's where we do it. So that's blast furnace and steel. That's important. Now I'm going to touch on hydrometallurgy real quick. I'm going to talk about leaching. Leaching is something that this chapter covers that I think is important that we are aware of. So if you are concerned about the environment, which you should be, right? We all live in this environment, so if we ruin it, we're kind of out of an environment to live. And the word that you're looking for there is extinction, right? If your environment goes away, you all die. So we should care at least somewhat about our environment. Then you might think, well, maybe all that like roasting and calcination and all that jazz, not a good deal, right? We're polluting, we're, wasting a tremendous amount of fuel in order to come up with this. Is there another way we can get metals? Well, yes, but as usual, other ways also have some drawbacks. So leaching is a process where you can dissolve the metal that you want using either an acid, a base, some kind of salt solution, or water if the metal containing compound is water soluble. Now, gold is one of the ores that we use leaching with in order to process. So you can obviously find gold in pure form, unlike things like iron, which is reactive and you're going to find oxides or, some kind of mineral in the crust. You can actually find pure gold in the crust, right? You find a gold nugget. But that is uncommon, okay? More likely, you're going to find gold in very, very minute quantities in some large batch of ore. And so in order to get it out, we spray it. And what we spray it with is sodium cyanide, NaCN. And NaCN, when you spray this thing down, the NaCN will dissolve it's like dissolved in water, and the cyanide molecule actually ends up attaching to gold, right? And you get this nice AuCN molecule, which is aqueous. You can dissolve it into water, and then now you have your gold bonded to your cyanide, and you can do just one more step. You eliminate the cyanide, get it away, and you're left with your pure gold in the bottom of your solution. Now, this involves something called a tailing pond. So what they do is they take these big concrete slabs. So this is concrete, and they pile up the ore on it. All right, so let's see if we can draw this here. So here's our ore, and they're gonna take a hose. That's like the worst hose ever drawn. There we go. And they're gonna spray the ore, right? And then we're going to catch the runoff, right? So we're going to get runoff, and that runoff is going to go into a tailing pond. Now, a lot of times, they leave that tailing pond sitting there in this open pit mine. And I'm not aware of any issues we've had in America with tailing ponds. I'm sure there's some out there that you could find. I am aware of one, though, that in Russia, where the tailing ponds, which have obviously cyanide in them, were unfortunately allowed to leak into the local ecosystem, and a tremendous number of organisms that were in the Danube River ended up being poisoned. So that's not great, right? Anyway, like I said, there is a drawback, right? If you can figure out how to safely deal with your tailing pond, well, then you can do leaching for gold. Once you have your gold cyanide species, you treat it with zinc, and you get zinc cyanide back and pure gold. There's your pure gold right there. Now, another example of hydrometallurgy is the Bayer process. All right, it's how we get aluminum ore. That's one that you can kind of look at in the textbook. All right, so I'll let you go read about that one. Now, the last one I want to talk about real quick in this video is electrometallurgy. Now, we're going to talk about electrochemistry at the very end of the year. That's the very last unit that we cover before the AP test. But basically, electrometallurgy is the reduction of metal ores using electricity. And there are 3 examples of this in your book. Sodium, this is how we get pure sodium. So we take molten salt, which obviously is extraordinarily hot, something like 1600 degrees Celsius, I believe. And we use electricity in a down cell. That's what this whole thing is called, the down cell. And that breaks apart the NaCl into chlorine gas, which is going to escape. And we get our sodium over here, which we then solidify and pour off, right? Now, it's really important in this down cell that we keep oxygen away from the sodium, right? And we keep water away from the sodium. So both of those things would be bad to come encounter with our down cell. Aluminum is also purified using electrometallurgy. So that's why I said go back and read about the Bayer process in your textbook, because it's going to involve a little bit of electrometallurgy as well. But this is what we use. It's called the Hall process. It was invented by a pretty young guy from France. There's a little inset in your book about him. I think he was from France. Pretty interesting story. But anyway, he uses cryolite, which is a relatively rare element. I believe it comes from, or mineral, I believe it comes from Greenland. And that is what is used to purify the aluminum and from the bauxite. So that's another interesting one. The last one the book talks about is copper. Pure copper rather, is kind of hard to come by. Copper, we find all the time out in the wild, right? It's a readily accessible mineral, or in mineral form. It's a metal that's readily accessible. But unfortunately, if you want to use it in electronics, you have to get rid of all the impurities. Otherwise, it's not actually very conductive, right? The more impurities that are there, the greater issues you can have with conductivity. So in order to get it purified, they use an anode, which is comprised of this raw copper, which has impurities. And they have a cathode, which has just a very thin, pure copper plate. And the active metals get oxidized at the anode, all right? But they don't plate out on the cathode. They don't bind to that pure copper. The only thing that really does is the copper itself. So as this runs, the cathode is going to get bigger and bigger and bigger, right? So like we start with this really thin piece, and then as it runs, it gets a little bigger as more and more and more copper plates onto the outside. So by the end, when you draw it up out of there, you have these layers of copper that's just purified copper, okay? Now, this has something just a little bit in part to do with the activity series, so you might want to brush up on that before we get to electrochemistry. All right, but for now, all that you really need to know is that copper is more easily reduced, and so it plates out, but the less active metals are going to deposit as a sludge down at the bottom. Now, those less active metals can be purified and used as well, so there's I guess a positive to this electrometallurgy there. All right, so that's going to be the end of this first video, okay? In the second video, we'll look more at the physical properties of metals. We'll look at the electron C model a little closer, and we'll look at some properties of metals, okay? So if you have questions about this, feel free to give me a shout, send me an email, and I'll be glad to give you guys a hand. Otherwise, I'll see you in the next video.